So let's now take a look into the effect of this non-zero Y22 or the non-zero GDS. Let's take the example of our good old common source amplifier, right? So let's see what's going to happen. Let's say this is a common source amplifier, and let's assume that it has been biased properly and all, right? So we know that floating battery is not realizable, but now we know that how to realize this floating battery using capacitors uh, and voltage dividers, right? So let's not bother with that. Let's say this is VI, VGQ, VDD. Let's say this is RD. Okay, so you have some quiescent current IDSQ going through the transistor. Okay, so what will be the incremental model of our of this stuff? The incremental model will be input is Vi that goes to the gate Vg. The transistor is replaced with the current source of value Gm times Vi, right? Gm times Vgs, but in this case source is grounded, so Gm times Vi. On top you have RD. RD is grounded, but is that it? No, right now, because we have a Y22, correct? We have a Y22, the new transistor model. So if I go back one more step, what was the old transistor model? The old transistor incremental equivalent model was, this is Vg, this is Vs, this is Gm times Vgs, right? So this was the incremental model for our transistor. So this was the port 1 and this was port 2. But now the new incremental model is, so this is the old model. So what is the new model? Taking channel length modulation into account with CLM, is input side remains as is. And the output side we have Gm times Vgs, and we have a Y22, or we call this GDS, right? So this becomes a new incremental model, so we have to use a new model here, right? So this is a GDS, and this is RD, right? So what do you think will be the output? What do you think will be V naught over Vi? Clearly RD and GDS, or in this case I should say 1 over GDS, because we are talking about a resistance here. So RD and 1 over GDS come in parallel. So essentially your V naught becomes minus Gm times Vi times 1 over GDS parallel RT, correct? Which can be also be represented as minus Gm times Vi by GDS plus G. Okay, so what do you think this expression is telling us? Clearly this expression is telling us that in the absence of channel length modulation, if we didn't consider channel length modulation, the effect would have been that the gain would have been minus Gm times Rd, but in this case the gain is dropping because the internal Y22 of the transistor, right, the GDS of the transistor is coming parallel to the output resistance. So in other words, the current that was coming from the GM, the current from the source, is now getting divided between its own impedance and the resistance on top, right? So what is the effect of channel length modulation, the effect of channel length modulation is the current GMVI is getting let me write it fully. The incremental current GM times VI is getting divided between GDS and G. This is leading to drop in the gain, right? So again, so what is the, if I sketch let me call this RDS instead of calling GDS. Let me call this RDS because we are talking about voltages. We are talking about resistances. This is VI, right? So again, what is the root? What is the issue? The issue is the current that is flowing out, right? The current, that's negative current that is flowing out, is now getting divided between this and this. Earlier, the entire current was flowing into RD, and we were getting a voltage of GM times RD times VI, or minus GM times RD times VI. In this case, we are getting a lower value of voltage, right? So what is the solution now? What do you think should be the solution? So in order to lead you to the solution, let me sketch this entire thing in a slightly different way. Then you will see that solution will probably become obvious. So let's say that this stuff over here, let me call it a current source, an incremental current source I in, right, with a internal resistance Rs, and we understand that I in is equal to Gm times Vi, and the resistance Rs is equal to Rs. What is the problem statement? The problem statement is I have this non-ideal current source and I want the entire current I in to flow into RL. This terminal of the RL is accessible, right? So I want the entire, so I want the entire of I in to flow into RL. What happens if I directly connect? There will be a current division between RL and RS, right? In other words, RL is loading the current source, correct? So, or rather the internal resistance Rs is loading the current source, and that is why we are having a problem. So that is why the entire of I in is not flowing into RL. So again, what is the problem statement? The problem statement is I need to push in this current I in, the total, almost the entirety of I in into RL, even though there is a internal resistance to this current source. So what I am asking is there a contraption that I can put in here that will do the job? Obviously, we have seen in the last couple of lectures few contraptions which can do the job. So what are we looking for? We are looking to transfer the current from one port to another without any division. So essentially, what do you want? We want a current controlled current source, right? We want a current controlled current source or a current buffer, which are the same things. If we have a current buffer, right, an ideal current buffer, input impedance is 0, right? An ideal current buffer, the impedance looking in is 0, right? Which means entirety of I in can flow in, right? Okay, so what is a current buffer? We have spent quite a lot of time in the last few lectures talking about CCCS, VCCS, and all sorts of current control sources. A current buffer in this case is essentially a common gate amplifier, right? Okay, so easy way to remember this is which port of the transistor gives you low impedance, the source, right? So looking into the source gives you the low impedance. So naturally, the source of some transistor should be connected to the input of the CCCS, right? So in other words, what am I saying? All I'm saying is, if this is my incremental circuit, all I am saying is, what I have to do, I have to put a current buffer. What is a current buffer? A current buffer. What is the incremental equivalent of a current buffer? Incremental equivalent of a current buffer is this, where the gate of the input gate of the current buffer is grounded, and this is, let's say this, I call this Vs. So the current will be Gm times 0 minus Vs, right? And obviously there will also be, well, I mean, let's not include the GDS for the time being, and there will also be a resistance RD connected to ground, right? Now you might turn around and tell me that we know that this current buffer will be realized, ultimately will be realized using a transistor. It's a common gate amplifier, right? It's a common gate stage. So if the transistor in the bottom doesn't have doesn't have zero GDS, right? It has some source resistance, it has some RDS. So we cannot also neglect the RDS of the current buffer, right? So there will be an internal resistance to this as well. So let's call this RDS 2, right? And where will this RDS 2 be connected? The RDS 2 will be connected between the ports of the transistor, that is the drain of the current buffer and the source of the current buffer, right? It's not that it's not between drain and ground, it's between drain and source. Okay, so in other words, what is this transistor? What is the let me draw it afresh so that we can do a proper analysis. So what will it look like? So this should look like, so you have Vi here for the original transistor. So let's call this Gm1 times Vi. There is an GDS1. You have a current buffer on top. The current buffer is the gate of the current buffer, right? Is grounded. So this we call as Vs. This will be Gm2 times 0 minus Vs. Similarly, you will have a GDS2, and then you will have this RD or GD connected between the top on the output side of the current buffer to the ground, right? And what is V0? This is the V0 that we are getting. So if we do an analysis of this, right? So let's, in order to do this analysis, what's going to be the V0? Let's Nortonize the circuit. So what will be the Norton equivalent? The Norton equivalent will be, output will be, so for Norton's equivalent, we need to short the first, in order to find out the ISC, right? So what will be the Norton equivalent? We need to find out ISC. Let's say I need to find out ISC. I need to find out R out. If I find that out, then I can put this RD here and 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 get it done, right? So essentially what I'm saying, you have an RD here. We are trying to find out the Norton equivalent of the box looking to the left. Okay. So what is ISC? How will you go about figuring out ISC? Let's copy this. So what would you do to get ISC? You short the output port, and I would like to find out the short circuit current in which direction? In the direction that in which I have marked ISC. So in other words, for ISC I am taking the current flowing out of RD, right, from the top. Essentially this will be the ISC. Okay, so let's find out ISC. So let's do a KCL at this node. We can do a KCL at this node Vs, definitely. But you can do a KCL at this node Vs, but a better way to approach this type of situations is to find out the impedance. So in order to do a KCL at any node, you need to know what is the impedance attached to the node, right? So sometimes it is useful to pause before you write out the full-blown equations to see can we ease our life by trying to figure out the impedance associated with the node first, and then go ahead and apply a KCL. So what I'm essentially asking is, what is the impedance looking up, right? So in other words, what I'm asking is, what is the impedance of this guy? So this is GDS2, this is GM times minus VS, where this is VS and this is shorted. What I'm saying is that what is the impedance looking up? What will you do? The same old. You apply a V test, right? And we find the I test. And again, this, instead of putting minus Vs, we can flip the direction of the current. This becomes GM V test, right? So what is the current through GDS2? This is GDS2 V test. So what is I test? So I test is GM plus GM2. This is GM2. GM2 plus GDS2 times V test, correct? So what is the resistance looking up? Rin is 1 by GM2 plus GDS2, correct? So what is the resistance looking up here? Resistance looking up is 1 over GM2 plus GDS2. So in essence, I can then ease my work and say that I will replace this stuff with a resistance, replace this entire contraption with this resistor, right? So let's do that. So if we do that, what we end up with, you see, this becomes this remains GM times VI, GM1 times VI, this is GDS1, and we have a contraption here, and the value of the resistance is, or in terms of conductance, if I write, this becomes GM2 plus, right? And we are trying to see what is the uh, what is the current that is flowing into GM2 plus GDS2. Why are we interested? Because note that whatever current flows in, through into this contraption has to come out from the other side, right? So in other words, what I am saying is, if we know the current that is coming out of this node or going into the node, I automatically know the current that is coming into that node, because this stuff is a black box or red box, the way I have sketched it, right? So whatever current is, because there is no other leakage path, there is no other path in which the current can escape. So whatever current comes in from the top has to come out from the bottom, or in other words, whatever current is going in from the bottom has to come out from the top, correct? So if that is the case, right, so this will be ISC, correct? So what is the current, that is, what is ISC? So KCL at Vs will yield the current that is coming into that node Vs is Gm times Vi, right? And what is current going, how much of it is how, so this is ISC essentially, right? This is ISC. So what will be ISC? ISC will be the original current Gm times Vi, Gm1 times Vi, whichever was coming into that node, will be divided between two conductances. The higher conductance will win. In this case, the ratio of the conductance will be Gm2 plus GDS2 by Gm1 plus GDS1 Gm2 plus GDS2, correct? So if we ensure Gm2 plus GDS2 is much larger than Gm1 plus GDS1, then what happens? ISC becomes approximately equal to Gm1 times, right? So this is the job of a current buffer, right? This is the job of a current buffer, where it will be able to isolate one part of the circuit from the other while transferring the current from one part of the circuit to the other, right? So this becomes the ISC. But what about the output resistance? So how do you find out the output resistance? So for output resistance, we do the same thing as we have been doing. What will happen to the input? Input will be grounded, right? Because in order to find output resistance, we don't bother about, we have to desensitize the input. What should we do at the output? We have to apply a test voltage, and we need to find out the test current, correct? So let's mark out the important aspects. So this is Gm times Pi, this is GDS1, and since the other gate is also grounded, I know this current is Gm2 times Vs, where Vs is this node, and this is also GDS2, correct? So let's try to figure out what will be the I test if I apply a V test, right? So if we know that what is Vi? Vi is 0, right? Since Vi is 0, so this goes off. So we are only left with this part of the circuit, okay? If we further know that, since the current I test is flowing into this contraption, since the current I test is flowing into this contraption, whatever is coming out will also be I test. If this is I test, what is Vs? What is the value of Vs? Value of Vs becomes I test times 1 over GDS, correct? So this becomes I test times 1 over GDS, or let me call it RDS1, right? So let me write it down also. RDS1 is 1 over GDS1. Similarly, RDS2 is 1 over GDS. Okay. So Vs becomes equal to I test times RDS1. Correct? So now if we apply a KCL at this node, right? If I apply a KCL at the drain terminal, right? KCL at PD, what should it do? What should it imply? It should imply that the current that is flowing in I test is equal to the two other currents. What is this current? What is the current flowing through GDS2? Current through GDS2 is V test minus Vs times GDS2, right? And what is the current that is flowing up, right? That is GM2 times Vs. So this becomes minus GM2 times Vs, correct? But we already know what is Vs. Vs is equal to I test times RDS1. So we can basically replace the same thing. So this becomes I test is equal to V test times GDS2 minus, if I take Vs common, this becomes GM2 plus GDS2 times Vs, where Vs is, make some space here, Vs is I test times RDS2, right? So now if I push everything on the other side, it becomes I test 1 plus GM2 plus GDS2 times RDS2 is equal to V test times GDS2, correct? So which essentially means V test over I test becomes 1 over GDS2 times 1 plus GM2 plus GDS2 times RDS2. So essentially your R out becomes 1 over GDS2 is RDS2, 1 plus, I have made a mistake somewhere, this is RDS1, right? This is ITS times IDS1, RDS1, correct? So this is, here it is GDS2, no problem with that. This is RDS1, RDS1. Okay, so this becomes RDS2 1 plus GM2 RDS1 plus GDS2 times RDS1, and if I remove the bracket, we get RDS2 plus RDS1 plus GM2 RDS2 times RDS1. This becomes the, okay. So let's sketch the network once again and have a brief look into what this actually means. So what is happening here? We have RDS 1 here, we have RDS 2 here, and this is Vs, this is Gm times minus Vs. And we are trying to find out what is the impedance looking from the top, right? So let's see whether this makes sense. So if I am trying to figure out what is the resistance from the top, then it's quite natural to expect that a term of RDS1 should appear, that is here, a term of RDS2 should appear, that is here, right? But we are having an additional term of GM2 times RDS2 times RDS1. So which among these three terms do you think will dominate? Clearly, the last term will dominate, because when a transistor is biased in saturation, right, we expect the Gm times the ideally, see, RDS2 is supposed to be infinite, right? Ideally, RDS2 is supposed to be infinite, because the Y22 is supposed to be 0. Because of some non-idealities, because of your channel length modulation, Y22 will not be equal to 0, but it will be a small value, right? So since we expect it to be a small Y22 to be a small value, we still expect RDS to be a large value, right? So in other words, we still expect Gm times RDS to be much greater than 1. So if that is the case, then we can say that this is the term that dominates, right? This is the term that dominates, and in the absence of the current buffer, what would have been the output resistance? In the absence of current buffer, the output resistance only would have been RDS1, but in the presence of current buffer, the output impedance has increased from RDS1 to this extra RDS1 plus RDS2 plus some additional resistive term, which happens to be the dominant term, right? Correct. So in essence, what is the small signal equivalent, or what is the Norton's equivalent of our network, of the current buffer network? So this is ISC. What was ISC? ISC was approximately equal to GM1 times Vi. What is R out? R out. So this I can say is approximately equal to GM2 times RDS2 times RDS1, right? If GM2 RDS2 is much greater than 1. That is a caveat. If it's not, then this is not true. If this is the case, then this will be true. And since in the transistor biased in saturation, we expect this to happen, hence you can say this R out is approximately equal to GM2 times RDS2 times RDS1, and we have our RD connected, and we are taking the voltage across the RD. So what is V naught? V naught will be ISC, right, minus ISC times RD parallel R out, which is minus GM times Vi RD parallel this guy RDS1 times GM2 times RDS2. So do you think the situation has improved with respect to a common source amplifier, or the situation has worsened? Clearly the situation has improved, because now the current division is happening between RD and an R out, which is multiple times of RDS1 in a common source amplifier, right? So in a CSAM, this would have been GM1 times Vi RDS1 and then RD. So instead of instead of RDS1, now you are having an amplified version of RDS1, right? So this I can say this is almost equal to R out, almost I can say this is equal to some amplified version, some A times RDS1. Note that this A is not the amplifying factor of the transistor, right? Not the amplifying factor for the common source amplifier stage, right? This is some factor, and that factor is, let me call this A2, right? So looks like instead of RDS1, now you have A2 times RDS1, where A2 is GM2 times RDS2, right? Since you have a higher resistance, essentially this contraption is a better current source than the contraption on the bottom. So in a nutshell, what did we see in today's lecture? What we essentially saw was there is a non-ideality in our transistor which we haven't been considering till now, and the non-ideality is the output impedance of the transistor. We have been considering that Y22 is 0 for our transistor, but as it turns out that is not. So there is some finite non-zero Y22, which means the output impedance of the transistor is not infinite. Right, till now we have been considering that the output impedance of the transistor is infinite. It's an ideal voltage control current source. As it turns out, it's not, because it has some finite output impedance. Now, if you have a finite output impedance, which is RDS1 in this case, and we want to use this contraption as a common source amplifier, so naturally the entire current, incremental current of GM1 times Vi will not flow into the output load that we purposefully have put, but there will be a current division between the internal impedance of the transistor, that is RDS1, and the output load, that will drop the gain of the transistor. So what is the solution? The solution is to put a current buffer in between. The current buffer to help the incremental current from the transistor to flow into the load R. All right. So if we put the current buffer in, what we see that we are able to make the entire contraption look like a better current source, because now the short circuit current remains almost the same under certain condition, obviously, and whereas making the output resistance higher, right? So this becomes a better current source, right? So this readily gives you a first hand example of the use of a current buffer in a practical circuit. Okay, so we'll stop here. In the next lecture, we'll see how do we actually bias this circuit. Ultimately, now it has become a two transistor circuit. So we are graduated from a single transistor circuit to a two transistor circuit in order to mitigate a non-ideality, right? So we will see how to bias this network in the next lecture, right? Okay.